My name is Justin Kruger. This is, I guess, more of a research update on some work I'm doing at the moment, which might get presented at a conference potentially later this year. But this is, I guess, just for me to start working out how I want to talk about it. So I'm looking at this idea of observability analysis for angles-only distributed systems. So I'll start off with the motivation behind this work, the kind of vaguely four-step approach I'm using for this kind of observability analysis, and finishing off with some next steps. So in terms of motivation, distributed systems enable lots of promising new capabilities for space technology, including at swarms at close separations, whether they're constellations at far separations, whether they're operating in Earth orbit or in deep space. But the issue with all of these varying regimes and the fact we're trying to localize multiple spacecraft in both an absolute and relative sense is that distributed navigation is actually very challenging, especially if we don't have GNSS available. And for some kind of theoretical navigation system, we obviously want it to be autonomous and self-contained in the sense there's not much human in the loop or ground in the loop interaction. We obviously want it to be accurate and robust and to be as general to different situations as possible. So I guess one favorable solution we look at in the lab is angles-only navigation, where we have cameras on observers in the system which obtain the bearing angles to target space objects, like in these images on the right here. And the nice thing is that cameras are ubiquitous and accurate and low-cost, low-power, low-mass sensors. And they can also navigate for non-cooperative targets. The issue is that observability can be weaker than other forms of navigation because when you think about what a bearing angle gives you, it gives you the direction to a target. It doesn't give you the explicit range of the target. It doesn't give you kind of an explicit absolute position measurement. So that means we can have unobservable or poorly observable modes in the system when we're trying to estimate its complete state from just these bearing angles. And the observability of the state is then heavily dependent on the properties of the system. So if we have things like different absolute and relative orbit geometries, if we have different measurement availability and quality, the different numbers of observers and targets in the system can all affect observability quite a lot. So we have kind of a problem here, right? We have an observability problem with angles-only observability. We have complex dependencies, and we have, if we want to apply this to a system, we have a design problem where we have some kind of navigation requirement we want to hit, and we also have some design constraints we have to meet. So the question is, can we easily assess whether an arbitrary system is observable? Can we then accurately estimate the achievable state uncertainty? And can we effectively design or optimize a system to actually achieve that performance in preferably an automated and easy way? So the broad approach for this has these kind of 4 steps in red, where we start off with some kind of navigation scenario and constraints. We then turn this scenario into some kind of measurement graph. We then do analytic observability analysis on this graph to say yes or no, is the system observable? We then do a numeric observability analysis, which is a little more detailed in terms of what can we actually expect our state uncertainty to be. And we feed all this into some kind of optimization framework to try and get optimal system parameters and to say, can we meet our navigation requirements with an angles-only system? So yes, there has been some prior work done here. So first of all, in terms of this analytic observability question, we have this lead derivative approach done by Hu et al., where they look at the graph topology and try and figure out whether the graph is observable for an angles-only system. The issue is that they kind of assume global instantaneous measurement access across the whole system, which isn't really, I guess, necessarily realistic for a kind of distributed navigation system. So we want to reformulate that a bit. The question 2, this kind of numerical observability analysis, some work on that was done by Adam Koenig, a previous member of the lab. However, there were some issues here where it didn't quite, include everything we might want to include in things like the amount of dynamics uncertainty and their effects on the measurements, things like estimation of auxiliary state components, and so on. And the question 3, this idea of optimization. Obviously, people have tried to apply multidisciplinary optimization to spacecraft systems before, but I haven't found much that's actually sort of explicitly focused on the measurement and sort of kind of navigation requirement. So we want to try and focus more on that aspect of the design. So first off, this kind of idea of analytic observability. we start off with this idea of a graph topology, where we represent the flow of measurement information in the system with a graph, where here we have 4 nodes, A, B, C, and D, which are objects, which might be spacecraft or bits of space debris or something, which have states to be estimated. And we have the edges directed from target to observer, which indicates the flow of bearing angle information from, say, target B to observer A. And we have different types of nodes. We have active nodes or observers which are performing navigation. We have passive nodes which aren't performing navigation. We have external beacons which have some kind of absolute orbit knowledge if they have something like GPS measurements available to them. And we have internal beacons which have absolute orbit knowledge but only through use of internal bearing angles. But we have this idea of distributed navigation where observers are only estimating the state of a specific subsystem, which in this definition is just themselves, their direct targets visible with their camera, and any connected remote observers. And so for remote observers, we have these sort of potential communication links where we say that observers share measurements if they have a subsystem member in common. So if 2 observers look at the same target, they share their measurements to get improved connectivity and observability. And once we kind of expand out all these remote measurements, we get these extra measurements in green. And we have these kind of different types of measurement edges in the system, which give us different types of information, depending on whether they are kind of local or remote, or whether they are measurements taken by a beacon or not by a beacon. So we want to kind of look at this system of edges and decide whether it is observable or not. So this is actually where some of that previous research comes in. Where these guys who all used a lead derivative criterion to decide whether a system was analytically observable. So let's say we have a state vector x for n spacecraft with some dynamics model f of x, and the set of measurements in the system z with this sort of measurement model h of x. And what we do is we compute these lead derivatives, which are just functions essentially of the measurement model and the dynamics model, and we stack them all into this big matrix here. And if this matrix up to some order q is full rank, then the system is called locally weakly observable. So this is kind of the same thing, but expanding out the partial derivatives. You can see that this might get quite annoying to compute algebraically if you have a complicated measurement model or dynamics model. But the basic idea is that this sort of measurements in this z vector kind of span the rows of this matrix essentially. So we have measurement information in the rows, and we take partial derivatives with respect to the state in all the columns. So we kind of want enough rows to span the columns really in terms of the information we have. And basically, in terms of the prior work, which looked at this from Keplerian dynamics, if the observer is estimating like the states of n spacecraft, we need at least n distinct bearing angle measurements which span all of those states to make this observable to third order. So I guess really what we can do then is list like a couple of examples of different types of system of 2 and 3 spacecraft, whether they contain beacons which have that absolute orbit knowledge, whether they have targets which are the passive objects, or observers which are the taking the bearing angles, and just kind of list how many states they have to estimate, what type of measurement they have to estimate it with, and decide whether the system is observable. It turns out if the system has a beacon in it, it is second order observable algebraically, and if it has at least 3 bearing angles for 3 system objects, it is third order locally weakly observable. So by applying this to the graph, we can kind of go through a bit of a loop and simplify it, where first of all, we kind of remove all these edges which, from the perspective of each observer, are related to objects outside their subsystem, because in that case, they're kind of adding more states to estimate, but they aren't really increasing the connectivity of the system so much. We can merge the remaining similar edges into single edges with increased weighting. And then we can actually promote nodes to beacons, which means they have the absolute orbit knowledge. If they possess some kind of self-loop, which means they are being measured by a beacon, and they have access to that measurement. If they possess this edge with greater than 2 weight, which is this idea where we have enough measurements to kind of span the state space, essentially, or where we have these kind of multiple measurements of the same target from 2 different observers. Or we have this third system, which is like, if you've got kind of a loop of observers looking at each other, in kind of a closed cyclic loop, then there's enough measurement information there to also close the observability state space. So in this case, actually, observer C gets promoted because it fulfills condition A and B. And then we keep doing this because it turns out observer C is now a beacon, so its measurements have a bit more importance in the system. So we can actually promote observer D as well to a beacon after going through this whole process again. And we keep going until the graph's unchanged. And we can say the complete system is observable if each node is itself a beacon, so it has its own absolute orbit knowledge, or is the target of a beacon, because beacons can estimate the relative states of their targets with only varying angles. So we have this condition where each node has to be a beacon or the target of a beacon, and also each measurement conferring beacon status has to be proper. And what that means is that the observer and target have to have different orbital planes and different orbit radii. If they do not, then the system isn't observable. But I will, I guess, remind everyone that this analysis assumes Keplerian dynamics. So in reality, we have perturbations which make things a bit more easy to observe. Okay, so we have this analytic system where we can look at a graph and we can say, with reference to specific observers, is their subsystem observable, yes or no? And is the whole system then observable? But for the purposes of actual design, we want to be able to estimate the observability of specific state components. And we also want to include things like perturbed dynamics and sensor noise. So we use this method developed by Adam Koenig, where we first of all look at all of the local measurements for one observer at a single moment in time. For example, all the varying angles of the targets they have in their camera. We then combine this as essentially the list of all observers they get locally, all measurements they get locally, and all measurements they receive from remote observers at one time. And then we stack this into essentially the same thing except across a set of measurement epochs, essentially saying we have a set of measurements over some time. If we have these measurements, can we estimate the state, or how well can we estimate the state? And to do that, we take the partial derivatives of this set of measurements with respect to each state component, with the idea that if specific state components and specific measurements are kind of more sensitive to each other, they are more observable because we can see those larger changes more easily. So what this kind of ends up with is this equation here, where we have R, which is the measurement uncertainty, is equal to this sensitivity matrix Y times the state uncertainty P. And we want to get P. The issue is we need to actually define R, this measurement uncertainty. So R actually depends on kind of three components here: the uncertainty from a priori or known information, the uncertainty from sensor noise, and the uncertainty from process noise. And the new kind of thing we're doing here is we're first of all including clock errors in the measurement times, and we also include the effects of dynamics or process noise. The way we kind of do this is we actually start from the state uncertainty. So we essentially compute this state uncertainty or state covariance sigma at each measurement epoch using some kind of predefined acceleration in RTN, which corresponds to our unmodeled dynamics. And we convert this state uncertainty sigma to the measurement uncertainty at that epoch by an uncentered transform. And the nice thing by doing this is that, by a fairly standard process, we get uncertainty correlated with the state and uncertainty increasing with time, which is kind of the properties we expect from having these uncertain dynamics on the system. Okay, so what can we actually do with this? First of all, we can use these numerical methods to validate those topological graph conditions. So I went about enumerating all of the possible 2 and 3 spacecraft subsystems. It turns out there are 335 valid graphs, which is quite a lot. But by applying the numeric method to this, we can actually look at the range of orbit uncertainties that I saw as a percentage of the semi-major axis for systems which fulfill at least one of those topological graph conditions for observability and systems which do not. And what we can see is that these proper systems which fulfill one condition or more are basically orders of magnitude more observable than improper systems which don't, which I guess suggests that these graph conditions are sufficient for observability and are a good way of doing this kind of simplified analysis. And also, I did this analysis for different types of absolute and relative orbit. So absolute orbits are either near circular or eccentric. Relative orbits are EI vector separated, so with like a swarm with a bit of relative motion. In-train orbits, which have very little relative motion. And constellations, which are very far separated spacecraft with very distinct orbital planes. And we can actually see that these results vary pretty significantly depending on what type of system you have. So the second, I guess, result here is we can use the numeric method to explore the applicability of prior research. So on the left here are 3 types of systems that were suggested to be observable by some prior work. We have these chain graphs, where basically each observer is looking and estimating the state of the observer ahead of it in a chain. We have a loop where we kind of just take the chain and close it up with an extra bearing angle. And we have this weight condition, which I've proposed here, where we have these 2 weighted edges in the graph. We say that's observable. So what we kind of notice is that these chain systems, this kind of top section of this table, the state uncertainty they have is actually really high if we have spacecraft at close separations, so kind of swarm scenarios, whereas they actually seem to be observable in the constellation in this rightmost column. So the chains are actually kind of dependent in terms of observability on what type of system we have. The complete loop system is generally pretty observable overall, but because I'm only assuming kind of this local connectivity and not global measurement access, they're kind of not something I really look at with my particular graph representation. And I guess the weighted edge system has pretty similar state uncertainties for no matter the situation. So I guess I view it as like a stronger observability condition than some of the previous research suggests. Okay, the last result here is looking at the numeric method to explore the observability of auxiliary state components, where I guess in terms of auxiliary state components, I mean things like the clock offsets between different spacecraft, because they need to be synchronized in terms of their clocks to exchange measurements. The ballistic coefficients between targets and observers, and the observer sensor bias in azimuth and elevation for the bearing angle. So these auxiliary components correspond to these last 5 rows here of this table, which show how accurately we actually think we can estimate those using these measurement batches. So you'll notice, I guess, roughly that the uncertainties are larger for these 2 on the left than these 2 on the right. This is because on the left we have a near circular orbit, and on the right we have an eccentric orbit, and it turns out eccentricity really helps with our angles-only observability. So we can estimate all of these extra state components simultaneously with our orbit states as well, but only provided we have, I guess, sufficient observability in the absolute and relative orbits to actually enable that. So in general, then we have, I guess, these broader conclusions where, as we might expect, angles-only observability is improved by variation in relative motion, absolute motion, more variation in relative perturbations between the spacecraft, which kind of corresponds to the amount of separation between targets and observers, and more variation in measurement baselines. So this corresponds to the constellation case, where we have spacecraft in very distinct orbital planes, and then they have very distinct geometry in terms of their measurements, which helps our observability. It's, I guess, a bit analogous to if you've done GPS navigation, this concept of dilution of precision, where you want GPS spacecraft in diverse points in the sky to decrease your uncertainty. So finally, observability optimization. This is actually kind of a next step because I'm currently working on it. But so far, we can turn an angled-only system into a graph topology. We can decide whether the graph is observable, and we can look at numerically determining the expected state uncertainty. So next, kind of achieving this state of enlightenment down the bottom here, is can we automatically optimize the system to achieve the state uncertainty requirement? So what I'm doing currently is developing a weighted quadratic cost function to look at the observability of the system, with some optional terms for things like the number of observers in the system, because adding an observer, for example, gives you more bearing angles, so you can improve your observability, but also adding another spacecraft is like a non-trivial cost, so we have to balance that in some way. We also have optional penalty terms, just things like making sure constraints are met, and currently I'm just applying gradient descent to this to optimize the cost, which works pretty well for what I've tested. The issue is that the observability is kind of complex and can be non-convex. So I think ultimately trying to optimize and characterize this cost function requires, I guess, a bit more exploration at this stage. But yeah, that's some future work for now. So yeah, thanks. I guess that was a bit of an intro to this topic, and I'm happy to take any questions.